Hello everyone. Today, we Synagates present you a deep dive into sorting algorithm evaluation by comparing their efficiency. For the evaluation, we use 11 datasets with 100,000 rows in each being sorted into an ascending order. The dataset that we use are a combination of ascending and descending order of integers, three sets of Gaussian flawed datasets that consist of both positive and negative 6 decimal places numbers. Next is order flawed, that is the dataset that's already sorted into an ascending order, repeated flawed that has repeated values, and the reversed order flawed that is in a descending order, the same flawed, and lastly, three sets of uniform flawed that randoms number from the certain ranges. The sorting algorithm that we evaluate are bubble sort, insertion sort, selection sort that have big O of n to the power of 2, merge sort, and quick sort that have big O of n log n. For this evaluation, we use MacBook Air M1 2020 16 GB.
Bubble sort. Bubble sort compares adjacent elements in a list, swapping them if they are of order until no more swaps are needed, indicating the list is sorted. As you can see from the result, bubble sorts are used a long time to sort when sorting false data, but not as long when sorting integer data.
This sorting algorithm contains two parts of the input array. Left-hand side is sorted part and right one is unsorted. In each iteration, insertion sort tries to insert the first or the last element of the unsorted part to the sorted part so that the new element is at the correct position, making the sorted list still sort. No need to iterate all values in array. As we can see from the table, same flow dataset just took the least CPU time around 0.02 seconds. In other dataset, it took average 3 to 4 seconds. Insertion sort is obviously faster than the bubble sort. The average time of bubble sort is about 17 seconds, whereas the insertion sort used only around 3 seconds. Because in each iteration, insertion sort has a condition to break the loop when meeting the sorted part, so it doesn't have to iterate through all the values and uses less time to process.
Next is selection sort. The selection sort is a sort that will find the smallest value among an unsorted partition, then swap it with the leftmost value on the unsorted partition. From table, we could say that this sorting algorithm is not good for the random float dataset, but good for the order one, or the one that has high possibility of being so, since it consumes the same range amount of time as the random one. And it's like that because the sorting algorithm only focus on finding the smallest value without checking whether the dataset is already sorted or not.
For the next sorting algorithm is merge sort. This sorting algorithm have three processes of sorting. First one is divide. The algorithm begins by dividing the unsorted array into two roundly equal halves. This process continues recursively, splitting its subarray in half until each subarray contains only a single element. An array with a single element is inherently sorted. Step 2, conquer. Once we have multiple subarrays with single elements, the algorithm then starts merging them back together. The merging process involves comparing the smallest element of each subarray and combining them into a sorted order. Step 3, combine the sorted subarrays are then merged together step by step. At each stage, the smallest elements are compared and placed into a new array, maintaining the sorted order. This merging continues until all the subarrays are combined back into a single sorted array. As you can see from the table, merge sort demonstrates consistent performance in terms of both CPU time and memory usage across various datasets, with only a few outliers. This consistency underlies its robustness and reliability as a sorting algorithm.
The last one is quicksort. Quicksort contains three components: pivot, I, and j. Initially, we set pivot as the last element, I as the position before the first position, and j as the first position in the array. We iterate j through the entire array except the last element. In each position of j, if the jth element is less than pivot, we increment I by 1 and swap ith and jth elements. After the iteration is completed, we increment I by 1 again and swap the ith element and pivot. Like this, the elements in the left partition of pivot will have lower values than pivots and higher for the right partition. The last step is to repeat all the processes for each partition. In the coding context, we recursively call the quicksort function with different parameters. Now, let's see how it does with our datasets. As you can see from the table, quicksort performs well for most datasets, except the ascending and descending, same reverse ordered and ordered float. Quicksorting relies heavily on pivot choice. A good pivot is when it's about the middle value of all values, because the partitions will be around the same size. If the following partitions keep at that, we get the least number of recursions possible, making it efficient. However, the four datasets that the quicksort doesn't perform well on lead to poor pivot selection, creating a lot of recursions, resulting in the slowness and more memory consumption due to a larger call stack. Next, I'll talk about interesting comparisons. As shown, the selection sort is the slowest and the merge sort is the quickest for the ascending and descending combination. In the memory context, merge and quicksorts, although fast, consume more memory since both use the recursion technique, creating a large call stack. For the ordered float, only selection and quicksorts perform poorly, and in terms of memory, it's the same thing as discussed in the previous slide. Lastly, for the same float, again, it's the selection and quicksorts that perform poorly. Memory consumption has nothing new to say. In conclusion, overall, bubble sort is the slowest and merge sort is the fastest. Still, bubble sort's performance is almost as fast as merge sort when it comes to datasets that have the same value throughout or that are already sorted. Insertion sort is faster than bubble sort and performs especially fast with those datasets as well. Overall, selection sort is slower than insertion sort and faster than bubble sort. Yet with those datasets, it doesn't perform faster at all. Lastly, quicksort is fast when the pivot choice is good, which is especially when working with the uniform float. These are our members, and that is all. Thank you so much for watching.